talking about transactions, structure of transactions, and hello all. In the previous lectures, I was talking about transactions, structure of transactions, and also how they are verified in different cryptocurrencies like Bitcoin and Ethereum. Okay, now we are going to talk about blocks and block mining. As you know, blockchain consists of some blocks, something like this. This is the first block, which is called Genesis block. Then the second block, the third, and this chain will be continued. Okay. Each block contains some transactions. Transaction number 1, transaction number 2, transaction number n. Maybe you ask how many transactions can be stored in one block. The number of transactions is not so important, but the size of the block is very important. In fact, in different cryptocurrencies, it differs. For example, in Bitcoin, each block must be less than 1 megabyte. In some others, maybe even the blocks must be smaller. Okay, so the miners must put some transactions inside the block in a way that the size of the block must be less than or smaller than a constant value. As I said, in Bitcoin, it's nearly 1 megabyte for every block. In addition to the transactions, each block contains the address of the previous block, something like this link. Okay, address of previous block. So if it's a block, we have this information: address of the previous block, address of the current block, and list of transactions. Okay, this address of previous transactions is something like this and creates a linked list, and this current address makes it possible for the next block to point to this. Okay, now I must explain how the addresses are created. The addresses, I mean the address of each block, is created in a way that nobody can tamper any transaction inside a block. Suppose that a miner wants to create a block containing T1, T2, Tn. Okay? To calculate the address of the current block, the miners uses the transaction ID. If you watch the previous recordings, about how transactions are created, which information there is inside a transaction, one of the information inside each transaction is transaction ID. If you can remember, the transaction ID was the hash of all the data inside the transaction. I explained it in the previous lecture. Also, I explained it through Python codes. Please watch it again if you cannot remember. Okay, so each transaction has a transaction ID. Now, the address of a block is calculated through hashing all these transaction IDs. So T1 ID, T2, I mean second transaction, okay? Third transaction ID, and finally the last transaction ID. All these information together will be hashed, and this hash represents the transaction address, okay? Represents the block address, okay? So the address of a block equals to the hashing using a hash function like SHA-256, okay? Hashing all this information, transaction IDs inside the block, will result the address of the current block. What's the benefit? The benefit is that if someone tries to tamper a transaction, so the transaction ID will be changed. If the transaction ID will be changed, so the current address of the block will be changed. So again, remember, a blockchain is something like this, okay? For example, the address of this block, the second block, is equal to the hashing of all transaction IDs. If someone tamper or change a transaction inside the block, so the transaction ID will be changed. If one of these transaction IDs changed, so all the hash, as you know, all the hash will be changed. And if all the hash changed, so the address of the block will be changed and the chain will be dropped from here. Will be disconnected. So using this approach, each blockchain prevents others to tampering transactions. In addition, to search a transaction in many situations, we need to know which transaction was stored in which block. To answer this question, searching a transaction inside different blocks, we need something with a better performance rather than this kind of hashing, okay? We calculate the address of a block using hashing of all transactions IDs inside the block. But we need also to search a transaction inside the block. To do so, instead of simply hashing them, we hash them using a data structure which is called Merkle tree. It's something like a binary tree, like a binary search tree, but containing hash values. So in this lecture, let's focus on the necessary data structures we need to construct blocks, especially Merkle tree. So let's continue by watching the related videos about talking these data structures. As I said, the most important part is in this lecture.
Okay, as I said, this whole topic is about the blockchain as a data structure and what it buys us. As a data structure, the blockchain is built upon other standard data structures. We're going to learn some of those now. We're going to actually also learn some data structures that don't directly come into the blockchain, though they kind of almost do. We're going to see a sort of family tree of data structures here. And when we put them all together, we'll have the blockchain, and we'll talk about why that's important. So that's what's happening in this topic. In this lecture, we're talking about three of the very most usual basic data structures that every computer scientist knows, which are arrays, linked lists, and trees, particularly binary trees. Now, if you have a computer science background, you probably know this already. In which case there's probably nothing for you to see here, but you probably can move on. But you might want to watch it anyway, because it may be a good review even if you know this stuff. So, right, as I said, we're going to look at some data structures. The ones we're going to look at in this lecture are arrays, linked lists, and trees. Okay, so an array is a linear data structure. We take data, we put it in a line. Or at least that's the way we think about it. It's in a line. And the things about an array is it's a fixed length, and you state what the length is when you create it. So you've got a kind of data sitting next to each other. All the data sitting next to each other are of the same type. And the data, a good thing about arrays is that they're accessible by an index of where they are on that strip. In sort of what we call random access. So if you think about, for example, in the old days when we used to do things with cassettes and with tape, if you wanted to get to something in the second minute of the tape, you had to run through the tape to get to the second minute. With digital things, generally, you can just go straight there. You don't have to run through anything to get to 2 minutes. You can get straight there. Actually, that's not necessarily true, but so you probably all have both mental models in mind. The things that you can go directly to the second minute, 30 seconds, or whatever you have, or one you actually run through to get there by fast forwarding through a recording or something. Okay, so the arrays of the type where you can get directly to, and it's the second minute, 30 seconds, as it were. Okay, so that's a good thing about arrays. There's some very good things about arrays. Okay, and so here's an array. There's an array of animals. So here's this idea of it being a line. We've got a line. In this case, we've got 1, 2, 3, 4, 5, 6 different places for data. We've got an animal type at each of those places, and we can access it at any point. And the way we refer to it is we have square brackets, and we have the number, and the number starts with 0. Computer scientists always stop numbering by 0. So A0 is cat, A3 is gorilla. So even though it's the fourth one along, that's A3 because we start counting at 0, right? Okay, so that's pretty clear, except for that out by one. That is a big cause of errors in programming, this out by one problem with the end item actually being in the end plus first position. It confuses even, well, maybe not the most experienced programmers, but it confuses people who've programmed before. So how does this work? When you set up an array, you tell the compiler you want to make an array of, say, 1,000 health records, for example. Doesn't have to be 1,000 health records. And what the compiler does is it essentially puts aside in the computer, it puts aside a continuous amount of memory. So that's just the right size for 1,000 health records. So you've got 1,000 health records size bit of memory put aside for this. It's all continuous memory. And you then define what goes into each slot, okay? Okay, so one problem with arrays is they can be very efficient in terms of space if you actually know how many items they're going to have in the array. But if you don't, you have to overestimate, right? So suppose you only have 500 health records, you don't know how many health records you're going to have. You have to give it the biggest number you might possibly have. So you're going to have to ask it to put away a lot of memory, which you're probably not going to use. So that is a bad thing about arrays. It is easy to access elements, that's a good thing. Hard to add elements. Let's just say add new elements. And not that easy to search, and we'll talk about that later. It can be under some circumstances. But that's an array. So that's an array. It looks like, well, this is probably not worth it. An array looks like this. We'll see more of this later, okay? Right, now, the next thing we're going to talk about is a linked list, okay? Now, what a linked list is quite a bit different from an array. Instead of thinking in terms of a block of memory that's broken up into places for each data point, we think of each data point as being its own node, okay? So the data points are independent in that way, but those nodes have two fields. One is the data, which I'm having numbers here, but it could be health records, it could be anything. It could be, of course, animal names again. And the second thing is what's called a pointer, and that points to the next node on the list. So what we've got is these sort of independent nodes pointing to each other until you get to the very end. It points to a null point. Oh, really? That works this time. It doesn't usually work. Okay, you point to a null thing at the end, and then you're done. So that's the whole. This is a linked list with two elements, and that's that, right? Okay. So the nodes then are independent. Have the data are independent nodes, and they point to each other. So it's sort of a linear structure as well, because we've got they go in a line, but it's got some very different properties. So we're thinking about it quite differently. We're not thinking of it as a continuous thing broken up. We're thinking of it as separate entities, and that works differently for the computer, right? When with the array, we told at the outset we said to the computer, the compiler, look, we're going to have an array with 1,000 elements. We don't do that now. We just say we're going to have a linked list, and then it grows and shrinks by adding and subtracting. So it's at different sizes. It's much more flexible in that way. So you can add things, you can subtract things, etc. And it changes its shape. It morphs. So it only takes up the space that it needs to take up, okay? Because if you get rid of part of it, it frees up the space. So it only takes up the space it needs to take up. You're not taking up 1,000 places for only having 500 records. It only takes up the space it needs to. That's the good thing about it. The data isn't contiguous. That's got some bad properties because with the array, because the data is near each other, there's such optimization things you can't do here, because you're just adding these at different times. There's no reason for them to be next to each other. Okay, it's hard to access elements. You have to go down the line to do it. But it's easy to add and delete elements, and I can have a picture of this, and this comes from Wikimedia. I think many of the pictures coming for us will come from Wikipedia, because they actually make better pictures than I do. I sort of feel that it's a cheat to use their pictures on the one hand, but they are better. So okay, so here I've got this linked list here which has the elements 12 and 99 in it. 37 is going to come in. I'm going to put it in between 12 and 9. All I've got to do is change those pointers. The pointers are very, very simple things. So that pointer from 12 no longer points to 99, it now points to 37, and I put in a new pointer that points from 37 down to 99, and that's quite a simple operation for a computer. So that's a really good thing. That's much better than what you can do with an array. Okay, we talk about are trees. I'd like to still be here, so I'm just trying to, if I can do this. Okay, so here's a tree. Okay, it's a bit like a linked list. Okay, right? So we've got trees are upside down from what they're like in the real world. The root's on the top, so 2 is the root. All the circles are called nodes, 2, 7, 5, they're all called nodes. Going down, they're called children nodes. So 7 and 5 are children of 2, 10, 6, and 2 are children of 7, 6, I guess, is a grandchild of 2, etc. Okay? The ones at the top, as I said, is a root. The ones all the way in the bottom are called leaves. So 5 is a leaf node here. Well, one of the 5s is a leaf node. Okay? So root at the top, leaves in the bottom. They could be different. They're not necessarily the same distance from the top. So that 2 all the way on our left is 2 from the top. The 4 is 3 from the top. They might be considerably more different than that. So being a leaf doesn't necessarily mean being the same distance from the root. It just means there's nothing below you. So that's a tree. That comes up lots of places. I'm just going to show you a few of them. This is called a pause tree. Okay? So what a pause tree is a tree that represents expressions, and we use them for expressions for when you're defining computer languages, for example. You use them if you're a linguist, you use them in defining natural languages. This is a pause tree for an expression which is a mathematical expression. So if you look at this, there's an equals at the top. So sort of the top level operator, it's a binary operator, it's equals, that's between f on one side and everything else on the other. What is on the other? Well, it's a fraction, and then the fraction has something on the top, which is the left, and something on the bottom that's on the right, and etc. So the times brings together, the times is an operator that brings together the leaves. The leaves are just letters, and the nodes that aren't leaves are operations. Okay? The same sort of thing happens when you're talking about natural language, where the leaves at the bottom might be words, and the things above them might be parts of speech or phrases. So there might be something like noun phrase, and then under noun phrase might be determiner noun, or determiner adjective noun. It's so things like that. So that's another pause tree. So that pause tree on our right is a pause tree for the expression on our left, which many of you will recognize as a gravitational equation. Yeah. So that's okay. This is a binary search tree. Okay. So first of all, the fact that it's binary means that no node has more than 2 children. So the top node has 2 children, the 3 has 2 children, the 10 only has 1 child, right? Okay, so that can have 1 child or 2 children. Sometimes, and for some things, you actually try to balance things, and we'll see that actually possibly later with Bitcoin. Okay, binary trees are an important part of what we're going to do. So suppose we're looking, and this is a search tree because this is arranged in a way to make it easy to search things. Now, obviously, again, like what I said about the medical records or animals or something, I've just got numbers here, but these numbers will be the key elements of a more intricate data set, perhaps. So I'm looking for the one that's got the key of 7. Look, I'm looking for something on here. So I start at the root. I start at the top. That's 8. Now the point is that 7 is less than 8. And that means I go to the left. And that gets me to 3. 7 is greater than 3, so I go to the right. So whenever I get something less than, I go to the left. If I go something greater than, I go to the right. So if I'm greater than it, I go to the right. If I'm less than it, I go to the left. Okay, and that's, I keep going till I get to the bottom. Okay, now So binary, it's binary, as I said before, because it has the most two children. And this is an amazing speed up in searching. It turns search from linear to logarithmic. What that means is if you assume you have 1 million elements to search and you put them in a search tree, to search through linearly, as we were describing before, in something like an array, well, if you're unlucky, you'd have to search all 1 million elements. On average, I guess you'd have to search 500,000 elements. With binary tree search, all you would need to check is 20. So the binary tree traverse is a lot faster than the linear search. Of course, it takes a lot of work to build up the binary tree. Okay, so that's that. We've learned about arrays, we've learned about linked lists, and we've learned about trees, and we've learned some examples of how you use trees. We're going to put several of these things together over the course of the next 2 lectures. The next one's going to put together some of the binary, not the trees, everything but the trees, and then we're going to put the trees in the one after that. Okay, so see you in the next lecture. Bye. Okay, we're now going to put together a few of the data structures we've already learned about, and we're going to do something called we're going to learn about something called a hash table, which is a fundamental thing in computer science. If you've done much computer science, you'll know all about it. But it's a way that data is kept for lots of applications, and we will learn about it now. And we will use various words and structures you've learned about already. And hash tables don't exactly come up in blockchain, but what we're going to do is going to move from this hash tables to something quite like hash tables, but a bit more complicated, called a Merkle tree. And that's what we're going to do in the next lecture. And that does come up. That's one of the keys, the key things in cryptocurrency blockchains, what have you. So we're going to learn, in this lecture, we're going to learn about hash tables, which is a very satisfying use of various things we already know about. And then in the next lecture, we're going to learn about Merkle trees, and then we're going to learn about how they're used in blockchain. So that's the kind of way we're going through this topic. Okay, so we're going to learn about hash tables. There we go, hash tables. That's right. This is an array, okay? So it's an array with eight spots on it. Remember, we talked in the last lecture about when you make an array, you say 2 things. You say how many slots there are for data and what kind of data is going to go in. This array is going to have data about animals, and not about species, but about individual animals. So we've got, for example, George the dog is one of our animals. Now, George the dog, probably we have a lot more data than just he's called George and he's a dog. We probably might have his address, we might have his vaccination record. We might have all kinds of things about George in that data. The data might be quite rich, but we're just referring to George the dog for now. And we'll see how that's all we need for what we're talking about in this lecture. So, okay, so here's some of the data we've got. We've got data about each of these animals. So we've got George the dog, Wendy the sheep, Mary the hippo, Billy the camel, and several others. And we can just put them willy-nilly, as it were, onto the array. So here's an array, and I've put each of these animals in one place in the array. So I'm assuming there's 8 animals. So that's an interesting assumption right there. So that's my whole database is 8 animals. Now that's not what we're going to be doing with the hash tables. So I'll tell you that right now. We can well have more than 8. But okay. So I'm just going to put them anywhere, and then if I alphabetize them, it would make life easier for some things, but I haven't. So if I need to get Sarah the goat's record, I go through. I look at the start, and I say A0. That's George. Is George Sarah? No. Is Wendy, Sarah? No, etc., etc., etc. Until I get to Sarah. That's called a linear search. We start at the beginning, we keep going in a line till we get to where we want to get to. So I search from these. You start there at the beginning and you keep going. Okay. So that's what we're doing with this array. But one of the things we have about arrays is indices. Is that useful to us? That's the question. Can we use those indices in a way that's useful? And maybe not. I mean, but why would I ask this question if the answer is really no? It's not obvious from what I've said so far how we would do that. The real answer is obviously yes, otherwise I wouldn't have asked the question. So that's what hash tables are for. So what we do is we define a hash function. You won't be too shocked to hear that. I mean, so who remembers what a hash function is? It's a function that takes inputs and makes outputs, and the outputs are all the same length. In these cases, the outputs are what we're interested in is the number that comes out of h. So h is a hash function that will give us a number. I mean, if it's not, we can do something with that. But so I'm going to assume that h of the individual animal is going to be a number, and I'm actually defining a particular hash function here. Okay, the hash function I'm defining here is I'm going to take the animal, say Wendy the sheep, and I'm going to h is going to compute the alphabetic position of the first letter of her species name. So not Wendy, sheep. Okay, and then I'm going to mod that by 8 so it'll fit into the table. Right? Okay, so that's a hash function defined here. It's not a great hash function, but it is a hash function. Okay, so h of George is 4 because George is a dog, and dog starts with D, and D is the fourth letter of the alphabet. Notice I'm not starting with 0 here. I'm saying A is 1. So it's not actually all the way to the left. A is the second one in. Okay? And that wouldn't necessarily be something, but it's the way to do it, but it makes life easier. H of Mary, on the other hand, is 0. So we do use the 0 because H is her species name because she's a hippo. And H, I think, is the 8th letter of the alphabet. I'm pretty sure that's right. Let's assume it is if I'm wrong. And therefore, since it's the 8th letter, when I mod by 8, I get 0. So Mary is H of Mary is 0. H of Wendy now, this is one I prepared earlier. Her species name is sheep, so it's S, which is all the way to 19th letter, again, if I did that right. So, and the 19 mod 8 is 3. So, assuming I've done these sums right, H of Mary is 0 and H of Wendy is 3. Okay? If I haven't done them right, well, just work with me on this. Okay, so here we go. We've got Mary. Whoops, I've got that wrong. So what should it be? It should be Mary 0, Wendy's 3rd, and George's 4th. So where I've got that second Mary should be George. So is that going to mess me up too much? Not too much. So we're just going to, I'll correct it in the handout, but just let's go with that. So that it looks like it says Mary, Wendy, Mary, but it really says Mary, Wendy, George. And I just want to say something about the various attributes about each of these animals, as I said, but the one that actually comes into the hash function is the species name, right? So that's called the key attribute. Just a bit of terminology. So now what happens when Billy the camel comes along? So I compute H of Billy. Billy's a camel. Camel begins with C. C is the 3rd letter in the alphabet. So Billy wants to go into the 3rd place where Wendy is now. So, okay, what are we going to do about that? Well, we can make it like some kind of board games where Billy goes into 3 and knocks Wendy out, but that's really not very useful, is it? So there's 2 answers to this question. And one of them is called the open address answer or the linear probe. And what that is that you put Billy into the next available open address, hence the open address name. And then when I look for Billy, I start at the position I would expect Billy to be at. In this case, we're the third position where Wendy is, and I go linearly along until I find Billy. There's the linear probe bit. So the open address bit refers to how we put it in. The linear probe bit refers to how we find it. So we would just therefore, so I would just put Billy in where just next to 2 along from Wendy. So this is getting, so it would be Wendy, then George, and then Billy. Okay, so that's one answer. It's called a linear probe. It's not great because you can imagine things getting filled up and it gets quite complicated, and then it's good if things are sparse enough. The other way is called chaining. And what chaining does is it replaces, it makes a linked list in that third position. So Wendy's now a node in the linked list that points to Billy on the linked list, as we learned in the last lecture. So we've got a linked list coming out of wherever there are collisions. So the hash table, which is really important, it's a way of putting data someplace where it's easy, relatively easy to find it. We use the array for the general shape of things, and that's good because we know the size of where the hash function is going to hash to. So remember this particular hash function I had, which was giving me numbers from 0 to 7. So I knew exactly how large the array has to be. That's a perfect position to be in if you want to make an array. The linked list, on the other hand, is good for the collisions because we don't know the size of the collision space, and it's easy to put things in. So we can use those linked lists there. So for the reasons I talked about before of the array being good for what the array was good for, we use the array. What the linked list was good for, we use a linked list. We have an array and linked lists, and we have hash functions. So we're using lots of things we already know. And this is all very good fundamental computer science. Okay, we haven't used trees yet. We're going to use trees in the next lecture. And the next lecture is kind of building again on all the things we know. Hash functions definitely, and trees. Not so much the arrays, but the linked list idea. The linked list idea comes in, the hash functions idea comes in, and the trees come in to what we'll call Merkle trees. And that's one of the fundamental things in Bitcoin's blockchain, etc. So it's really important we learn that, and that's what we're going to learn in the next lecture. See you there. Okay, we've learned about several data structures so far on this topic. We've learned about arrays, linked lists, and trees, and then we looked about hash tables, which we're using hash functions to make tables that were use both arrays and linked lists. If you remember, the arrays kind of gave you where you put things, and then the linked list dealt with collisions. Now, of course, the hashes we were using there were not cryptographic hash functions. In the cryptographic hash functions, we don't really have collisions, or we assume we can't find collisions, and collisions, therefore, even though they exist, are not an issue for us. They're spare, they're sparse, and we don't have any way of controlling how to find them. So we kind of assume, and nobody has. So we sort of can ignore them, okay? So that's about cryptographic hash functions. We're going to talk about cryptographic hash functions again now in the data structure we're learning about just in this topic, in this lecture. It's called Merkle trees. And Merkle trees are data structures that are built around trees and cryptographic hash functions. So 2 things you know about. Merkle trees, okay? So Merkle trees are named after Ralph Merkle, who invented them. I'm not sure quite how long ago, but I should have looked that up. But sometime before Bitcoin, that's for sure. So there's lots of other applications for Merkle trees, and we'll talk about some of them. They're all to do with how you put things together and making sure things are safe. And we'll give a couple of that. We'll give a Bitcoin. It will be our main application, but we'll also look at other ones. One other one at the end. Okay, Merkle trees are a cryptographic data structure. So they're a data structure with cryptography built in. They're trees. They're usually binary trees. They don't have to be binary trees, but the ones in Bitcoin are, and in fact they're so carefully binary is so that if you get an odd number, you recreate, you copy the last one again to make an even number, because you want to have that remaining as binary. Okay, and they use cryptographic hash functions. Okay, right. Here's the motivation. Okay. So this is the motivation for what we're going to be doing. We want to put 1,000 transactions in a structure called a block. We have 1,000 transactions. We're going to put them down in some kind of list or something and make a block out of it. A bit of data. We can think of it as an array, I suppose. In that way, it's a block. The way I'm thinking of it now, just a list of things. Okay. Now, an important part of what we're doing, perhaps the most important thing we're doing, is we want to be able to tell if the block has been tampered with, right? We don't trust anybody in this universe, so we need to trust. In cryptography, we trust. All others pay cash. We trust cryptography to make sure that nobody's tampering with anybody with anything. We don't trust anybody on their own. And more than that, I want to be able to be assured my transaction is there in an untampered way. So it's not just that no tamper, that I want to make sure that my transaction is actually counted there. So that's something that I need to do sometimes. So, okay, here's a solution. I've got 1,000 transactions. I'll number them T1 to T1000. I'll take a cryptographic hash function, and the one that's used in Bitcoin is called SHA-256. We talked about that before. And we apply it to each of the transactions, and each TI will become HI. So I've now got a hash of the transactions. My hashes are H1 to H1000. And I might, to keep track of them, to get one number to respect them all, I'm going to take a hash of all that. So I'm going to concatenate them and take the hash, and that's going to give me a number I'm calling big H, which is the hash of that whole thing. Now there's some practical problems here. That's a quite big thing that thousands of hashes put together. You might want to do it in pairs or something, and that would be interesting. But in theory, it's something you could do. Now, what happens if somebody changes H100 or T100 actually? Changes a transaction or the hash of the transaction. What happens? Well, when you do that hashing again, you don't get to big H. So you can tell there's a problem. So it's a bit like what we were talking about when we were talking about parity checking. You can tell there's a problem, but you can't tell where, right? Okay, it's a problem. So if you want to know, if you want to check if a particular thing's been tampered with, that's a lot harder. Okay, so remember what binary trees did for search. Trees are going to do the same thing for us here, more or less. Here's a Merkle tree. Okay, right. So how does this work? If you look at any node except for the bottoms, it's got two children. It's got a hash as the data added that node, and that hash is applying our cryptographic hash function to the pair or the concatenation of the two children. And the information in the two children, until you get to the very bottom, are also hashes. So until you get to the bottom, you're taking hashes of hashes, right? Okay. So we're taking hashes of hashes, and each time we're taking a hash of the concatenation of two hashes of the one for each of the children below it. Okay. So we're taking these hashes, and they're themselves hashes until we get to the bottom. The leaves at the very bottom are the data, which in the cases of Bitcoin are transactions. Okay, so we have the transactions laid out. We have 1,000 transactions, and each one of them is hashed to get us the layer above it, and then they're put together in pairs, as in that picture there, to get So we've got 1,000 at the bottom layer, we've got pairs, we've got 500 pairs at the layer on top of it, right? We just put them together. Then there's 250 and then 125, etc. Yep, okay. So there we go. Good. Okay. So the hash in the top node represents the whole tree. So that's what's called a digest. I don't know if I've used that word with you before, but the digest of the whole tree. Now that doesn't mean from that number or that string I can recreate the tree. It just means if somebody else says, here's the same tree, I can do the hash function and find out if they are the same tree. It's the digest that can represent the tree, but it's not enough information to get back to the tree itself, at least not in an obvious way. Okay, so we use that top node as a cryptographic signature for the whole tree. Okay, so here's where the tree structure comes in. And by the way, this picture and the one before both come from Wikimedia. I generally use Wikimedia because they create you know what I mean, because I have access, I'm allowed to use them. So anything I don't draw tends to come from Wikimedia. So if I look at the following hash tree, I want to prove that the third leaf is in the final hash. So I'm looking at the third leaf, the one here that's called HYI equals 2. Okay, right, you get that? So what I'm going to do is thinking what I have to do to check that it's there. Okay, so what do? Well, that leaf, if I think of what happens in making the tree, that leaf gets hashed with it becomes hashed up to A0, and then A0 gets put together with auth 0 next to it, and gets hashed to become A1. So A1, the information in A1 is the hash of A0 and auth 0, and A0 is the hash of the transaction. Yeah, I might say that again. So A1 is the hash of its children who are A0 and auth 0. A0 itself is a hash, it's the hash of the transaction. So is auth 0 as it happens. So auth 0 is the first bit of information you'd have to give me that I don't already have. If I've got my transaction and you give me auth 0, between me them I should be able to get up to A1, right? Okay? Now, if you give me auth 1, I look at auth 1, I've already got A1 because I've done the hashing with A0. I've got A1. If you give me auth 1, I can hash auth 1 and A1 concatenated together and use the hash function, and that'll get me to A2, right? So now I'm up to A2, right? So, and you've given me, so I'm almost done. I'm one off the top, and you've only given me 2 hashes, auth 0 and auth 1. And you're now going to give me auth 2, because that's the one that gets hashed with A2. So you give me auth 2, and I get hashed with A2, and that gets me up to the top. So I can now check that what I've got there is the top. If what I've got there is the hash at the top, then I know that my transaction was put in correctly. Got that? So I've got that. Everybody knows that A3. That A3 is the digest for that whole tree. Everybody knows A3. It's kind of public knowledge. You've given me, just by having those 3 other hashes, auth 0, auth 1, auth 2, I was able to check. So I just needed those 3 things to do. So instead of dealing with 8 things, I only had to deal with those 3, but that doesn't sound like a big difference, but once you get to 1,000, it's pretty big. So if I were doing the same thing with a tree with 1,000 leaves, is used in those systems as a way of keeping track of upload different bits of it at the same time from different sources. And that's how things like BitTorrent work. And the Merkle tree is used in those systems as a way of keeping track of Now I'm just going to talk very, very briefly about another Merkle tree application, torrenting. Suppose we want to upload a large media file, like say a game. The games are quite large. It would take a long time to download a game or upload a game from someplace, right? So what you do instead is you might much more quickly upload different bits of it at the same time from different sources. And that's how things like BitTorrent work. And the Merkle tree is used in those systems as a way of keeping track of how those bits fit together. Okay? So that's just another application, an earlier application than Bitcoin. Okay, next stop, blockchains. Blockchains as a data type, getting ready for you to do some implementation. And so I'll see you at the blockchains. Bye for now. Welcome. We're now going to talk about the blockchain as a data structure. This is getting ready for your implementation. Okay, right. So the blockchain is going to use the Merkle trees. You won't be surprised to find. We'll see how that works in a minute. So this is a particularly short lecture as it happens, even though it's got the name of the whole module in it. But it's just very, very short, and it's kind of setting you up to do some programming. Okay, so what is the blockchain? We've said a lot of this before. The blockchain is a distributed ledger. I mean, what the phrase people use is an immutable distributed ledger, and we'll talk about the immutability later in this lecture. Okay, so what does that mean? It's a long list or ledger of transactions. That's one way of looking at it. It's just an enormous list of transactions. But the list is broken into sections called blocks. Okay, and everybody in the network has access to this whole ledger, to all these blocks. Okay, so that's the distributed part. The distributed part is everybody in the network gets access to it. The ledger part has got all the transactions in it, and the immutability we'll see about in a bit. The blockchain part, the block is just the section of transactions. Okay, so that's all the words we're thinking about. In practice, it's not quite like that. What happens is the blockchain actually grows one block at a time. And the way that works is people, really nodes, compete to build the next block on the chain. So they solve a puzzle, and that's the part of what we're going to do in the next topic, talk about what that means, how you mine, and that's called mining. You mine a block by solving a puzzle, which is what's called proof of work. That's all a part of the next lecture, the next topic. So people compete, or nodes compete, to be the ones to build the next block, and the reason they do it is that they get paid to do it, right? The winner gets paid, they get the fees. Remember, the transactions frequently left a fee behind. Those fees go to the miner, to the person, the node that makes the block, and until now you also get paid for making the block. You get a fee for making the block, which will disappear at some point. Okay, and then the other thing about this, and we'll talk about this much in this lecture, is each block refers to the one before. That's the other bit about it. So what's in a block? Okay, so the block is mostly transactions. So we've got the transactions in a block, say around the they're pretty variable. Okay, so they're actually arranged as a Merkle tree, right? Let's build Merkle here. Okay, and a header. Right, okay, so that's to be LE, not Merkle, but, okay, so transactions arranged in a Merkle tree and a header. Okay, so what's in the header? That's what the rest of this lecture is about almost. Well, one thing that's really important in the header is the hash of the previous block, okay? So that's what it means. So it's a little bit like pointers, it's a little bit like linked lists. Each block has it's like having a pointer to the next block. It has the hash of the previous block. It's got the information, all the information about the previous, it says what the previous block is, essentially, and all the information. So that's really important, or at least a digest of the information, because it's got a hash of it, okay? That's where the immutability comes from, because what happens if somebody changes a transaction in a block? Well, then it messes up the hash of that block, which means that in the next block, when it refers to the previous block, that'll be messed up too, and the one after that, and the one after that, and so on. It just percolates all along. So it's a big mess. So if you can't go back and change a transaction without doing a lot of work, if you change one thing, you have to change a lot of things, and that's is kind of like this. These are style we're making, right? So there's two hashes here. There's a hash of the previous block, and there's a hash of my transactions arranged as the top of a Merkle tree. That hash is the hash at the top of the Merkle tree. Okay. So the picture of the data structure is kind of like this. These are stylized Christmas trees, blue for Christmas, and each of them is a tree. It's supposed to be a Merkle tree with the transactions in a block, and so each one of them represents a block, and they kind of point through the use of that hash. They kind of point to the previous block. Okay. So the transactions are sort of arranged in this tree, this chain of trees. There's a way of looking at it. Okay, there's a sort of chain of trees. That is the way the transaction. We'll learn more in the next topic, because this is about solving the puzzle. Solving the puzzle to do the mining means finding a nonce with a particular property. find a nonce with the right properties. And everybody on the network will and that's really all I want to say at this point, I think. Told you it was a short lecture. And okay, that's it for now.
Okay. Now we know what's Merkle tree. Now we know what information are inside each block. And the next step is talking about the mining process and the solving the puzzle. Okay. See you next in sorry.